Hi everyone, welcome back to Dave's Math channel. This is my 6th video in a sub-series on derivatives of my first series on first year calculus. And today I'm going to derive a formula for differentiating polynomials, arbitrary univariate polynomials. And the formula is written in the middle of this slide, but I'm going to go over it. So let's begin. So first I want to talk a little bit about polynomials. So what is a polynomial? Well, the simplest type of polynomials are called univariate polynomials. It turns out you can have polynomials of arbitrary degree. You can have a polynomial or a polynomial with an arbitrary number of variables. But in this case, since this is first year calculus only concerns functions of one variable. So the simplest types of polynomials are called univariate polynomials. Sometimes we just call those polynomials if we know that's what we're talking about. But I wrote down the general form of a univariate polynomial. It's just it's a weighted sum of powers of the variable. So it has the form an. If it's a degree n, then it looks like a sub n, x to the n plus a sub n minus 1, x to the n minus 1, and so on all the way up to a1x plus a0, where these ak's, these are what are called the coefficients of the polynomial. They're just constants. So you can just think of this as the sum of a bunch of terms that involve constants times powers of x, and they're all finite powers of x, and they're all finitely many terms. They're all non-negative integer powers of x. So that's kind of the definition of a univariate polynomial. We can also write this equation using summation notation. I don't know if you guys are familiar with this notation. You probably are, because I think most people learn it in high school. But here's the summation notation, 1b. You just write this funny symbol. This is called a sigma, Greek letter sigma. And then you put the subscripts and the superscripts on these sigma just tell you the lower and upper limits of the sum. So here we're going from k equals 0 to n, where n is the degree of the polynomial, and we can write 1a this way. It's just a more compact notation. So we can write it. Sum as k goes to n of a sub k x to k. It means exactly the same thing as 1a. You just don't have to write as many terms. So anyway, and now I've just told you what polynomials are, univariate polynomials. How do we differentiate them? Well, the formula is pretty simple for differentiating univariate polynomials. It turns out that what you do is you're basically just using the power rule for each term. I mean, that what happens to so for instance, the first term of f of x was a sub n x to the n. Well, I think we remember from the power rule that the derivative of x to the n is nx to the n minus 1. Here we're multiplying by a sub n, so we really just get a sub n times x to the n minus 1. That's going to be our first term. Similarly, our second term, since our original polynomial had a sub n minus 1 x to the n minus 1, again using the power rule, the power goes down by 1. That becomes x to the n minus 2. But then the power also gets multiplied by the coefficient a sub n minus 1. So now we get n minus 1 times a sub n minus 1 times x to the n minus 2. I think you see how this goes. So, and then you should notice one other interesting thing here. The constant term always disappears. Notice there's no a0 in this formula for a prime of x. That should make sense. Remember what I told you? That the derivatives of constants are 0? So the constant doesn't play any role. It never does. You can always add an arbitrary constant to any function, and the derivative will remain the same. Derivatives don't care about constants that you're adding. So the a0 goes away, but every other term survives, and the powers all go down by 1. That's basically the rule. You can write this again using summation notation. Looks a lot prettier if you write it that way. It's just the sum as k goes from 1 to n. Remember, we could get rid of the term k equals 0 because that one went to 0. So now we have the sum as k goes from 1 to n of k a sub k times x to the k minus 1. That's the rule. And how do we prove this rule? Well, I think I kind of gave you the idea how to prove it. We have to use linearity. And remember the way I talked about linearity before. It only applied to functions with two terms, but you don't have to have just two terms. You can have as many terms as you want. I mean, this is what I call generalized linearity, where you have a finite number. So it has to be a finite number of terms. But linearity holds for a function whose a weighted sum of any finite number of terms. So what you do is you just to differentiate the whole expression, you just pull out each constant and differentiate each function in each term. That's all you have to do. And we already proved it works when m, I'm calling m the number of terms here. We already know it works when m equals 2. And the way you can prove this in general is you use something called mathematical induction. This is a very powerful form of proof in math. If you're not familiar with it, I think most people learn this in high school, but in case you're not familiar with it, the way it works is you always, to prove that some fact is true for every integer, m or n or whatever your variables you're using, you first prove a base case. And in this case, the base case is m equals 2. And we know that m equals 2 works because that was what we had before. That's just what we called ordinary linearity. But now we want to prove it for bigger m as well. So the way we do that is we assume that it holds for some m. And we already know it holds for m equals 2. And then if we can prove that whenever it holds for some positive integer m greater or equal to 2, if we can prove it also holds for m plus 1, then we will prove that it holds for every positive integer m. And the reason we do is because you're basically, it's like you're climbing up a ladder. You're studying at m equals 2, and then you prove that if it holds for m equals 2, it holds for m equals 3. But we've proved this for general m. That means it also that if it holds for m equals 3, it holds for m equals 4. If it holds for m equals 4, it holds for m equals 5. So on. So this is the proof by induction. And the way we do this is we're assuming it holds for some value of m. So now we let f of x. We're just going to use two functions here. I'm going to let f of x be the sum of the first m terms, the weighted sum of the first m terms. And now I'm going to let g of x be the weighted sum of the m plus first term. So now we have two functions, and now we can just apply the sum rule. So we know. So now what we're really trying to do is we're trying to differentiate this entire sum, and the way we do that, you can see, is just equal to the derivative of the sum of f of x and g of x. But we already know how to do that. We know the sum rule. It just says the derivative is f prime of x plus g prime of x. But now we can use our induction hypothesis to say that the derivative of f prime of x is just the weighted sum of the derivatives of f1 up to fm, and now the derivative of g prime of x, we can use the scalar multiplication rule to say that that's equal to c sub m times fm prime of x. So now when we add everything, we get what we want. We get the weighted sum of the first m plus 1 terms. So we've already shown that if we assume the induction hypothesis holds for some fixed m, it must hold for m plus 1 as well. That completes our proof. And we're not quite done, because I've just proved generalized linearity. Now we have to apply it to polynomials. Well, at this point, it's pretty simple. I mean, all polynomials are is they're weighted sums of powers, not non-negative integer powers of x. So all we have to do here is we kind of have to relabel everything. We have to relabel our indices. Because don't forget that the powers are going from 0 to n. That's why I used m instead of n for the generalized linearity. We want to change our variables. So now we're letting n equal m plus 1, I believe. And we're letting j, we're relabeling indices. J is now going from 0 to n. So we want to let cj be a sub j plus 1, and c and then m equals n plus 1. If we do all that, we just substitute everything. And we're also letting f sub j, or sub, yeah, what is it? I have to read this. F sub k of x is x to the k minus 1. If we make all those substitutions in the generalized linearity formula, we do recover the rule for differentiating arbitrary polynomials. Pretty easy to see. Anyway, that's the proof. And I think it's good. I think it's a good idea to finish with some examples here. So it's really pretty easy to differentiate arbitrary polynomials. Remember that all you're really doing is you're just applying the power rule and linearity. So let's just do some examples here. The first example, consider the polynomial f of x equals 3x squared plus 4x plus 5. What do we do? Well, we're starting with 3x squared, and we use the power rule on x squared. Derivative of x squared is 2x. We have to multiply the coefficient 2 by 3. That's going to give us 6x. That's what we're going to get for the first term. Second term, we're differentiating 4x. Derivative of x, that's like x to the first. That's going to be 1x to the 0, or just 1. So we're just going to get 4 for that term. And the 5 we don't care about because that's a constant. So the derivative, f prime of x in this case, is 6x plus 4. And every other example you look at is like this. So let's just do a little more practice. I'm going to go through each of these examples. So second example, we have f of x equals 8x cubed minus 12x squared plus 6x minus 1. How do we differentiate that? Same way. 8x cubed, remember the derivative of x cubed? We multiply by 3. The 3 becomes a constant in front. We multiply by it by 8, giving us 24. And the power goes down by 1. So our first term of the derivative is 24x squared. And now we look at the second term. This time it's negative. Remember that polynomials can have negative as well as positive coefficients. So our next term is minus 12x squared. And our exponent's 2 in this case. So we multiply the constant minus 12 by 2, giving us minus 24, and the power goes down by 1, so we get x the first, or x. So the second term is going to be minus 24x. The last term we're going to get comes from 6x, and remember the derivative of x is 1, so the derivative of 6x is 6. And now we're done, because all we're left with is this constant minus 1 at the end. We don't worry about that. So that's how to differentiate the second one. Third one, and there's two different ways you can write polynomials. Some people write polynomials, or sometimes you see polynomials written where the exponents are decreasing. I think that's the more common way to write polynomials. You usually start with the highest order term, but sometimes you do it backwards. You'll see polynomials written the other way a lot too. So here's a polynomial where the terms have increasing powers of x. So now we have f of x equals 1 minus x plus x squared. And how we differentiate that? Well, the 1 we don't care about because that's just a constant. So we leave that one alone. So now we have minus x, which is really just minus 1 times x to the first power. And remember, x, the derivative of x, it's easier to remember the derivative of x is 1. So the derivative of minus x is going to be minus 1. So that's our leading term of the derivative, minus 1. And the last term is x squared. That's easy. Derivative of x squared, just using the power rule, is 2x. So we're left with minus 1 plus 2x. And then for the fourth example, I guess we have another polynomial here with increasing powers. But notice we're skipping some of the powers. This happens for a lot of polynomials too. You might get a lot of terms with coefficients of 0. Usually don't write those down. But you can have a polynomial where you're skipping powers. And this is an example of that. As a matter of fact, the only powers that appear in this particular polynomial are even powers. This is an even polynomial, or even function. You probably learned about odd and even functions. They have interesting geometric properties. Even functions, if they're polynomials, it's easy to remember these in terms of polynomials, because an even polynomial is a polynomial where all the powers are even integers. And an odd polynomial is a polynomial where all the powers are odd. But there's also odd and even functions in general. They don't have to be polynomials. And what that means, an even function by definition is a function such that f of minus x is equal to f of x. So it looks symmetric with it's symmetric about the y-axis. The y-axis is a mirror of symmetry for the function if you graph it. That's true of polynomials as well. And odd function is a function such that f of minus x is minus f of x. And these functions are symmetric about the origin. They have a different kind of symmetry. It's not a mirror symmetry. It's a twofold symmetry, twofold rotational symmetry. Odd functions have that property, and odd polynomials as well. Kind of useful facts to know. You'll see a lot of odd and even polynomials. So example 4 happens to be an even polynomial. If you graphed this thing, you'd see that it was symmetric about the y-axis. So anyway, our polynomial for example 4 is 4 minus 8x squared, or 4 plus 8x squared minus 5x to the fourth. And we use the same rule. Remember, 4 is a constant. So when we take the derivative, we get 0. 8x squared, again, we bring the power 2. We bring that out, multiply it by 8. That gives us 16. And we decrease the power by 1. That gives us 16x. And the last term, minus 5x to the fourth. Do the same thing. Multiply the constant by 4. That gives us minus 20. And to reduce the power by 1, that gives us minus 20x cubed. So our answer is 16x minus 20x cubed. You might notice something kind of interesting here. Notice that the derivative is odd. And this is always true. It turns out the derivative of every even function is odd. And similarly, the derivative of every odd function is even. Those are kind of those are kind of useful facts. I think it's kind of obvious for polynomials, but it's true for other functions as well. Kind of a fun fact. And the last example, this is one where the constants, remember the constants don't have to be integers. Constants can be arbitrary numbers. Usually you see arbitrary real numbers. You can even have functions where the constants are complex numbers, imaginary numbers. I think in this course we're not dealing with imaginary valued functions or complex valued functions. That's something called complex analysis. That's something you usually don't get into. Most undergrads don't even really learn complex analysis. I don't think I first learned it until I was in graduate school. That's like fourth year calculus. It's fun stuff, but it's way beyond what we're doing. So we can assume every function we're going to study in this course is a real valued function. So these are all real, but our first two coefficients are irrational. We have pi. I think you guys all know pi is an irrational number. Not only irrational, it's also transcendental. But anyway, our function is f of x equals pi x squared plus the square root of 2 times x. What is that? Minus 3. And so we use the same rule. We multiply the constant by 2 because that's the power of x. So f prime of x is going to be 2 pi x. That's the first term. And to differentiate the second term, square root of 2 times x. Remember, the derivative of x is 1. So we're just going to be left with the square root of 2. And we don't care about the constant term, minus 3. So we're done. So that's how you do that. Like I said, it's pretty easy to differentiate polynomials. And you'll see polynomials a lot. So now you know how to differentiate polynomials. So you've already learned a big chunk of what you need to know about calculus. So anyway, that completes my video for today. Thank you for watching. Long live math, and I'll see you guys next time. Bye.